Assalamualaikum and a very good morning to all my students. And how do you do, guys? I hope all of you are doing very well. Okay, so for today's lecture, I'm going to proceed with our chapter 1, still in chapter 1, and it is about stereoisomerism or tacticity. So let us recall what we have learned last week. So it is about isomerism, right? So what is isomer or isomerism? Okay, so isomerism, it have different molecular configuration for molecules, polymer of the same composition. So the polymer have the same composition, but it has a different configuration or the arrangement ataupun susunan dia. Okay, susunan dia berbeza, but dia punya composition is the same, right? So stereoisomerism is defined as the differences among isomers that arise as a result of the various possible orientation of their atoms in space. So the possible steric configuration of an asymmetric vinyl polymer can best represent by drawing the chain in its extended chain planar zigzag conformation due to the lowest energy conformation. Okay, what does it mean by configuration and conformation? Okay, conformation is the flexibility or the rigid types. Okay, conformation is the order that arises from the rotation of molecules about the single bond. Okay, all the molecule it have its orientation. Okay, so the conformation is the order that arises from the rotation of molecule, right? So the term configuration and conformation basically we use to describe the geometrical structure of a polymer. Okay, so the polymer it has its own structure. So these two terms we use to describe its structure, the polymer structure. So the terms for configuration is actually the order that is determined by chemical bond. The configuration of a polymer it cannot be altered unless chemical bonds are broken and reformed. Okay. So when a chiral center is present in a polymer molecule, different configuration or optical isomers are possible. So there are three possible different configuration, which are atactic, isotactic, and syntactic. Okay. So configuration is actually under stereoisomers, right? Which is isotactic, syntactic, and atactic. And we have geometrical isomer. Okay, we have stereoisomer and geometrical isomer. So for geometrical isomer, it's about cis and trans. Just I mentioned last week. Okay, kalau stereoisomer, dia duduk bawah atactic, syntactic dengan isotactic. Okay, so let's look at what is atactic. Okay, atactic is polymer with no preferred placement of substituent group. So atactic is types of the stereoregularity isomer. Okay, so the arrangement is random, right? For isotactic, the substituent group lie on the same side of the plane formed by the extended chain, mean that the group lies in the same direction. Okay, so for the last one, syntactic is the substituent groups regularly alternate from one side of the plane to the other. So the placement of those methyl group is alternate. Okay, we'll look at the structure. Okay, for isotactic, the benzene ring is placed on the same side. For syntactic, benzene ring is alternately placed on the backbone. Okay, dia selang-seli kan. For atactic, it is randomly organized or randomly placed on the backbone. Okay, this is the styrene monomer, and when undergo the polymerization process, the stereoisomerism may be in this conformation, right? So the importance of stereoisomers have the important effect on the chain packing. For example, polypropylene. Okay, we can see that for isotactic type of polypropylene, it has a high crystalline because the regular chain can pack closely together. Okay, why this happen? Okay, I repeat. For isotactic, all of the methyl group are on the same side of the chain. Okay, iso. It is the same side. All the methyl group are head to tail. Okay, all the methyl group are head to tail, and all the groups are on the same side of the chain. Okay, for the atactic. Okay, atactic. It has a difficult to crystalline. So the soft it produces soft non-crystalline polymer, and the boiling point slightly lower than isotactic, which is 75. So the sequence of the crystallization point means that if isotactic, it have more crystalline structure than syntactic, and syntactic has higher crystalline than atactic. So atactic is a tendency to be amorphous polymer. So atactic it has the methyl group or R group are randomly organized. The methyl group are both into and out of the plane. It has no real registry, okay, no real placement. So the two additional point cannot readily interconvert between the stereoisomer. Okay, the bond must be broken, and most polymer are a mix of stereoisomer. So often will become a predominant. For the conclusion, isotactic PP is has highly crystalline, and when the highly crystalline material, it can retain at high temperature because the boiling point is high. Okay, so isotactic is crystalline and atactic is amorphous. Okay, so amorphous, its boiling point is quite lower than crystalline. Look at the crystallinity. What is the crystallinity? Okay, I'm sure that you have learned during your diploma. And okay, the arrangement and the interaction of the chain has a considerable effect on the properties of the material. So the most significant factor is whether the material is crystalline or amorphous. The crystalline polymer or amorphous polymer can be classified according to their morphology. So crystallinity is the degree of long-range positional order exists in a three-dimensional structure. So in a crystal structure, the atom or molecule are arranged in a regular periodic number. So crystalline state is the area in polymer where the chain are packed in a regular way. So there is the crystalline and amorphous region of a polymer. Okay, basically for the crystalline state, it is well packed. Okay, so for both amorphous and crystalline area, they are in the same polymer. For crystalline, there are regular chain structure and they have no bulky side group. So for more crystalline polymer, they will tend to become more stronger and less flexible because the properties are very rigid. Okay, crystalline polymer are basically strong, but it has low impact resistance. Okay, so when the increase in the crystallinity region, it will increase the rigidity of the polymer. It also will increase the melting point and less affected by solvent penetration. Okay. Okay, we look at the polymer morphology. The molecular shape and the way molecules are arranged in a solid are important factor in determining the properties of a polymer. Okay, generally we have two type of morphology in a polymer. Okay, basically polymer will have these two region, right? Mana-mana polymer memang akan ada dua benda ni. Mostly dominated by amorphous or crystalline region. Okay, so we have crystalline region which is order structure. Okay, this is the structure which is ordered or well packed structure. Okay, and this one is the amorphous region which is the coil structure. Okay, we look at the crystalline and amorphous structure. Okay, so the crystalline is regular. Okay, the irregular structure for amorphous. Okay, we look at this is the isotactic polypropylene viewed through a polarized microscope. Okay, this is the crystal structure, which is called as a spirolite. Okay, spirolite is of a partially crystalline polymer. Actually, this is the recorded version in the mid 1950s. Okay, when the people start to crystallize the newly available, which is the Ziegler high density polyethylene and also polypropylene. Okay, from dilute solution, and it observed the crystallite, the one in the left, right? The structure on the left. So in the crystalline structure, they have a lamella, and in the lamella they have the crystalline and amorphous structure. So we call it as this one is the lamella crystal, and on the lamella crystal it have a crystalline region, amorphous, and also the spirolite surfaces. Okay, so the big picture here, cycle here is the we call it as spirolite. Okay, we look at the next slide and look at the amorphous region. Okay, the amorphous region is a section that consists of randomly coiled and tangled chain with no significant order region. So it has lacking positional order. And the amorphous polymer exhibit the amorphous region, and it has a transparent unless rendered opaque by the additive. Example of the amorphous polymer are PMMA. Okay, we have a tactic polystyrene. Okay, a tactic means what? It is random polystyrene. Okay, random placement. We have polycarbonate, polybutadiene, and also polysulfone. Okay, mostly amorphous, it cannot be packed together. Okay, if the polymer is highly branches or it have a high pendant group, so the amorphous polymer will increase the soft of the polymer. Okay, so the Tg also decrease, and the solvent is easily to penetrate into the polymer, amorphous polymer. Okay, we look at the crystalline. Crystalline is a section where the crystallites arrange themselves into spherical order region. Okay, crystalline polymer exhibit the crystalline region due to the chain entanglement and irregularities within the chain. Polymer are never 100% crystallized. Okay, so can polymer achieve 100% crystallinity? No. Okay, no. There is no 100% crystalline polymer unless we create it in the lab. Okay. So the example of the crystalline polymer, okay, we have Kevlar, okay, we have the aramid, um, we have polypropylene. Okay, we cannot say that the crystalline it is the 100% crystalline, so we call it as the semi-crystalline. Okay, so some semi-crystalline polymer are polypropylene, okay, polybutylene terephthalate, okay, polyethylene terephthalate PET, polyether ether ketone, okay, PEET, okay, PEK. Right. We look at the polyethylene glycol, PEG. Okay, PEG we have a molecular weight about 35,000. Okay, Fluka is the name of the company produced that chemical. Right. Look at the morphology of crystalline polymer in the next recording version. Okay, thank you.